What's up guys? So this is our problem. We are required to draw the shear and moment diagram for the cantilever beam. First, we should get the value of our reaction and moment due to our fixed support at point C. Next, we should get the concentrated load from our uniformly varying load through its area of the triangle. The formula of the area of the triangle is 1/2 times base is equals to times 1.5 meter times the intensity or height is 8 kilonewton per meter. Then we'll calculate 6 kilonewton. I'll cancel out this. Then we should get the concentrated load from our uniform load through the area of the rectangle. Which is base times height. Base is 3 meter times height, which is intensity of 8 kilonewton per meter, equals to cancel out the meter and equals to 24 kilonewton. To find the location of our concentrated load from our triangle, we should use 1/3 times base, which is 1.5 meter, which is equal to 0.5 meter. Then for the location of our concentrated load in rectangle, which is in the middle of 3 meter, which is 1.5. So this is now our concentrated load from our uniformly varying load, which is 6 kilonewton, and for our uniform load we have concentrated load of 24 kilonewton. Then we can get the summation of our moment at point C. We assume positive clockwise rotation in the summation of moment at point C is equals to 0. In summation of moment, the applied moment here is 15 kilonewton meter. Since it is in a clockwise rotation, so this is positive 15 kilonewton. Then our 6 kilonewton here is in counterclockwise rotation. It is negative kilonewton, negative 6 kilonewton times its distance of 3.5 from point C. Then in our concentrated load in rectangular, it is also counterclockwise, so it is negative 24 kilonewton times its distance from point C is 1.5 meter. Then and our MC is also in clockwise direction, so it is positive MC equals to 0. And we should transpose the value of 15 minus kilonewton times 3.5 meter minus 24 kilonewton times 1.5 meter to the right side. Then we get our moment at point C is equals to 42 kilonewton meter. And to find the value of our RC, we should get the summation of forces vertical is equals to 0. Then assume upward direction is positive. So RC is upward, positive RC minus 6 kilonewton and also negative 24 kilonewton is equals to 0. Then our value of our RC and then we should transpose it the right side at positive 30 kilonewton. So this is our value of our RC. And we set our horizontal line as our 0 reference, and above the horizontal line we have a sign of positive, and below the horizontal line is negative. At shearing diagram, also at moment diagram, at above horizontal line we have positive and below we have negative. So in shearing diagram, the value of our shear at point A is 0 because it is in moment force. And then point B, which is VB, we have a triangular bearing load which is 6 kilonewton downward, and it is equal to the value of shear point B, so it is negative 6. And in VC at point C, we have applied force which is 24 kilonewton concentrated load from B to C, and since it is downward it is negative 24. Then since we have preceding shear which is negative 6, and we can subtract it to negative 24, then our shear at point C is negative 30. Then for our shear diagram, we have shear at point A which is 0, start here. Then for our shear at point B, we have negative, so the sign negative here is here. Negative 6. Then at shear at point C, we have negative 30, so here negative 30. In our uniformly varying load, we have a slope of 1 degrees. Then for our uniform load, we have 0 degrees. Then in shear diagram, we should add 1 degree slope from our load. Then this will become 2 degrees. Then 0 degrees plus 1 is 1. Then if it is in 2 degrees, this is the curve. When it is increasing to negative. And for negative 6 to 30, negative 6. So as we see here, our RC is going upward, and it is with the location of our value of our shear at point C going downward. So we should add the preceding value point C, which is negative 30, to the value of RC, which is 30 kilonewton, and it is equals to 0. Then here in our moment diagram, in moment at point A, we have 15 kilonewton meter rotating clockwise. So we assume here at positive sign. So 15 is positive. Put here point A. Which is 15. Then for a moment at point B, we subtract the preceding moment, which is 15, minus to the area of shear at point A to B, which is in geometric shape is spandrel. So the formula of the spandrel is one-third times base, which is 1.5 times height, which is 6, and our value of our moment at point B is 15 minus 3. So calculate, it will become MB is equal to 12. So 12 is here at point B, 12. Then moment at point C, which is we should subtract the preceding value of our moment, which is 12, minus the area of from B to C, which have a geometric shape of trapezoid, and its formula of 1/2 times base plus base, which is 30 plus 6 times height, is the value of here, which is from B to C, which is 3. So our value at point C, moment at point C, is 12 minus 54. Then 12 minus 54 is equals to negative 44. So negative 44 is here. Negative 44. Then in moment diagram, we should add the slope from shearing diagram plus 1. So 2 degrees plus 1 become 3 degrees slope. Then from B to C, we should add 1 degrees plus 1 degrees, so it's become 2 degrees. Then since it is in 3 degree slope, the curved line here is from 15 to 12. Then 12 to negative 44 is just like this 2 degrees. As you see in the diagram, the value of our MC is 42 kilonewton meter, and it is rotating clockwise, and it is in positive sign. So then we should add the preceding moment value at point C, which is negative 42, and it is equal to 0, and that's how we correct the diagram if our diagram is correct. That's all. Thank you.